let's look at some of the synthesis of carboxylic acids that we've seen before. So we have seen how we can make these, and we first saw this way back in our alcohols chapter, and we saw the Jones reagent, right? So often what we call this mixture was Jones, acidified sodium dichromate or chromic acid. So when we take a primary alcohol and treat it with Jones, we get a carboxylic acid. And if you remember, if we want to stop that reaction and not go all the way to the carboxylic acid, we had to use pyridinium chlorochromate. So what that did was stop this reaction at the aldehyde. We'll use both of those reagents a lot in the next 3 chapters. So hopefully you remember those and see their utility as we go through this chapter. The other thing we can do is we can do oxidative cleavage. So oxidative cleavage is just breaking this bond. So remember, we're kind of taking a knife and we just cleave that bond here. It's warm, concentrated KMnO4. Sometimes basic conditions are present there, and then in that case you would have to do an acid workup. But what it does is it takes that bond and it essentially opens it up. So I want to write this out a little bit odd here. So that bond that used to be here is going to be broken, and what we're going to get is we're going to get a carbonyl right here. Now that carbonyl cannot be oxidized further because there's no H atom there, but we're also going to have a carbonyl here, and that has an H that can get oxidized to this. So it's a kind of a weird way of drawing this molecule, but I think it's often easy for students to draw it like this because you can kind of see where the double bond was, and I think it's easy. But anyway, you could straighten that out if you really wanted to. So alkynes also react with warm concentrated KMnO4 in the same way, and in this case you would form 2 carboxylic acids because you can't have any substituent off of these positions, right, to make a ketone, for example. So in this case, you're going to break this thing into 2 parts. That part right there is going to become benzoic acid, and then the other part is this, right, with your COOH on the other end. We've also seen oxidation of alkyl benzenes. So we saw that back in chapter 17. We can do side chain oxidation is what that was called, right? And then we go through, depending on the situation, sometimes you have to do acid workups, but you end up with a carboxylic acid functional group there as a substituent on your ring. Now, a little review here of reduction of carbon dioxide with Grignard. So this reaction involves using CO2 in a Grignard reagent. So if you recall, we have here an alkyl halide with magnesium. So that makes your Grignard. And remember that this thing reacts like this. Right, so in essence, that's coming around here with CO2, and we see an electron flow like that. Okay, so what that would form then is your COO minus right there that gets protonated with your 3rd step acid workup to make your carboxylic acid there. So side note on this one, if you see CO2, so if you see CO2 as part of a multi-step, you should be thinking of something like this occurring. Now, the other reaction that's an observed reaction that we're going to see in this chapter is hydrolysis of nitriles. So I like to cover this mechanism in chapter 21 because it's introduced there. It's better, it fits in better in that chapter anyway. So the observed reaction though takes an alkyl halide or just an alkane that has a good leaving group. So it could be a tosylate. And then we add sodium cyanide. So remember guys, that's an SN2 reaction, right? We saw that back in chapter 19. And that would make here this, which is a nitrile. So nitrile. Now that nitrile can undergo hydrolysis under acidic conditions. And under acidic conditions, it's acid catalyzed. We form an amide. Right? Now, if we take that same mixture and we heat it up, then you get a carboxylic acid. Right? So the only difference between stopping here versus here is the use of heat. And we'll look at that mechanism in our next chapter. Now, the other thing we can do is we can do a base catalyzed hydrolysis here. So a base catalyzed hydrolysis takes hydroxide and water, it makes an amide, and then we could go through and make a carboxylate, and then with an acid, you would make your carboxylic acid there, right? So again, kind of looking at that, you have a nitrile with hydroxide, water, and heat, takes you to a carboxylate. A nitrile with heat and acid takes you to the carboxylic acid, right? So two different methods, or reaction conditions, I should say, that end up with the same essential product. And again, that mechanism is going to be reserved for chapter 21. Now in this next section, we're going to look at reactions of carboxylic acids and start to look at some of the derivatives here too. Now, there's going to be a pattern here. So we're going to have this Z group here, and that Z group can be all sorts of different things. So here's a carboxylic acid. That would be an acid chloride. A larger group here would be an anhydride, an ester, and an amide. And we'll see nitriles show up in this thing too through our example that we saw before. Right, with our nitrile hydrolysis, they can make carboxylic acids and amides depending on what your conditions were, right? So the idea is that the nucleophile essentially comes in here and replaces the Z group, and that Z group gets kicked off here and is lost. So this is a nucleophilic acyl substitution. So what we're going to do here is carry out this reaction, and we're going to see this a lot as we go through 20 and 21, as we can have two conditions. We can have acidic or we can have basic conditions. So what I want to look at first with you guys is just the basic conditions here. So let's take a look and see what the mechanism looks like here. So why don't we take an ester? So we have our ester here. See a reversible reaction, and then let's throw a base in, like hydroxide. Now remember that carbon has a delta plus on it, right? We saw that when we drew out those resonance structures, if you remember one of our previous lectures. So the nucleophiles are gonna be attracted to that position. Now what that gives us is our R group and our carbon, oxygen and a minus charge here. And then I'm going to swing around this OR group to this top position here. And then down here below, you have your OH. Right? So what happens here is this structure will continue to react, but this is called a tetrahedral intermediate. And in essence, what's going on is this oxygen here is really, it's kind of like a weightlifter that's holding these, these electrons above their head, these weights above your head. There's pressure. So there's pressure up there on that oxygen. And just like water that's up in a dam, it really wants to go down to a lower energy. So it wants to come back down. Right? The weightlifter really wants to drop its weights. Right? The electrons want to come back down, and they would like to reform a carbonyl. And they do. So these electrons are going to come around, and they're going to do this. Okay, and what we're going to form here is another intermediate. It's really our final product, with the exception of our conditions continue to cause this reaction to to move a little bit further. All right, and then plus RO minus. All right, now that OR group can leave. It is a strong base. I know we've said in the past that strong bases make bad leaving groups, but that's true for SN2 reaction. So we were real clear on we need to have a good leaving group for an SN2 reaction to occur, right? A weak base. So this doesn't stop, because what we have here is we have a carboxylic acid that's been formed, and we're in a basic solution. So really what we're going to do is we're going to have hydroxide come around here and grab that H. That'll form our carboxylate, right? So this part's easy, acid-base reaction. And then if we want our final product there, all we would have to do is carry out another step. So here's your step number 1 over here. Step number 2 would be your acid work up there. All right, so that would give us our carboxylic acid back. So anyway, it's an important step that you'd have to carry out in a lab. All right, I want to talk to you guys real quickly about the reaction energy profile for this thing. So what I want to look at is just a different reaction. So let's just do a little side note here. Okay, here we have our energy, and here's our reaction coordinate. Okay, so what we're going to do here is we're going to look at the reaction of an ester. So let's go over here and let's do that. Okay, but what I want to use here rather than hydroxide is I want to use NH2 minus. Right, so what's going to happen here is the NH2 minus is going to come over and it's going to attack this position here. Right, so we're starting off energy wise. I'll just draw a line right here, and we're going to come up and land somewhere about right there. Right, now that intermediate is going to be an oxygen with a minus charge. I'll put in those lone pair there. You'll have your methoxy group there, and then NH2 right here. So remember, that's your tetrahedral intermediate. So that's an uphill energy change. Now what happens next though is that we do this, and we're going to kick off that. Right, so we're going to come up, and then we're going to sink down here to this lower energy. And these are all relative, so they're not exact energies. But what we would get down here after that is you're going to get your carbonyl back and your NH2, and then here CH3O minus there. So I just wanted to show you that that step, having that leaving group leave here, is actually an exothermic step in this particular reaction. All right, now what about acidic conditions? So acidic conditions are pretty straightforward, and we've seen reactions kind of like this before. We're going to see a lot that follow the same general principle. So let's start off here with that same ester. Okay, so here is our ester. Now acidic means H3O plus, so I'm going to write here H plus slash H2O, but we need to remember that this of course is H3O plus, right? So I'm okay with you just writing H plus H2O here. So one of the principles that we need to remember is that under acidic conditions we can't have negative charges on structures. So we don't tend to do that. So what we're going to do is we're going to take our most basic oxygen, which is this guy up here, and we're going to protonate it. That'll give us this, with our plus charge here. And then that's going to give us 2 additional resonance structures. So the first one's going to be that fellow, plus charge here, and then your OR down here. And then the last one is going to take the lone pairs on that ester linkage and convert those into a double bond. Oh, we get that. Right, so at that point in time, what we're going to do is we're going to continue our reaction. So we have our resonance structures in place. Now we're in the presence of water because we have H3O plus here. So water is going to come around here and attack that carbon. Right, so it makes sense, right? Look, that's where that plus charge is. And then we're going to swing those over back to our oxygen there. Right, so what we're going to get there is our R group, our carbon. Here we have our OH, the original OH that's there, right? And then over here we have our water that has come in with a plus charge. And then lastly, down here, your OR. Now we need to deprotonate. So we're going to take H2O, and we're going to grab one of these H's. That'll give us our R, COH, another OH over here, and then an OR down there, right? Now this thing is, we start off with an ester, and your ester has essentially consumed a molecule of water, so we call this thing an ester hydrate. Now we're not done, we need to continue this reaction. So what we're going to do next is we're going to take this molecule, right, and we're going to add another proton. Now we're going to do that down here. So it's true, sometimes students wonder, like, why can't it add here? Or why can't it add there? It can. If it does, then you just go backwards, right? So remember, the reactions are reversible. So we just want to move in a forward direction here. So we're going to take our proton and we're going to eat it up with the lone pairs of our oxygen of our OR group. All right, so what that's going to give us here is your R, OH, OH, and down here you're going to have an OR, H plus. So the key is that this group has to get protonated before we kick it off as a leaving group. Right? Otherwise, it would have a negative charge. It'd be an OR minus. Right? And then kind of moving down here, we'll start swinging down this direction. We're going to take a set of lone pairs here and swing around and do this. And then we're going to kick off our alcohol here. So you're going to get ROH, and then we get our other structure, which is our carbonyl with an H on it like that. Now, I'll point out to you guys here too, that has resonance. I don't want to draw them all out again, but there's two other, right? Just like we saw in that first set of resonance structures. So we'll assume that you can do that at this point in time. And then the last step here that you have is that you have a deprotonation. So we're swinging around, grabbing this H, and putting that those electrons back on oxygen as a lone pair. So that'll give us our OH group back. And then down here, you'll have your carbonyl.